read the chapter on work sales inside the textbook, the guy is, or whoever wrote it, I guess it's a guy, got some things a little bit wrong from the terms that we actually use in the trade. Sensors. Now we use sensors all over the place, except any automated machine. Most automated machines depends on sensors, and of course, a sensor is a device that converts a physical stimulus into an equivalent electrical output, right? So y'all probably need to take some pretty good notes because the book has some problems in this section. And they don't cover some of the, he doesn't cover some of the sensors that we need to understand. And we're not going to get into the electronics or the physical way these things work. Basically, we'll just look at the type of sensors and see what they do in this class. Of course, we know a sensor is a device capable of responding to, but it's a device that converts a physical stimulus or stimuli into an equivalent electrical signal, right? That'll be okay. And it's also called a transducer, which I'm not really sure if the book covers that term or not, but it's in your glossary that's out there. And we went over to different things. Some of our sensors, the book doesn't even cover these at all. These are manually operated sensors, but that's what they're doing. They're taking a physical stimulus, which is us doing what? Pressing them or switching them and converting it into an electrical equivalent. We use these guys all the time. I came in this morning and I turned on the lights. Well, that is a sensor because it sensed what? It sensed me. So we have all these different types of push buttons and switches and selector switches that fall into the category of sensors. Are we okay? By the way, y'all can go ahead and turn in your. We talked about this. Everybody okay here? We have analog and digital. Y'all understand this?
I'm not clear on it.
Analog is something that is continuously varying. So, if you got a thermometer at your house, that is analog, because it has the ability to continuously vary, right? The temperature thing on your air conditioner or your heater would be considered digital, because you set it, the switch at a certain temperature. So it doesn't, understand what I'm saying?
Yeah, so
A light is digital. So these light switches are digital. They're either what? Off or on. I've got one at my house, so it's got a little thing on the side of it where I can control the intensity of the light once I turn it on. That would be analog. So analog is the ability to continuously vary over a range. So if you look at my dimmer switch on my light, I can turn it on, but once I get my light, once I got it as bright as it's going to get, I can't get any brighter, and once I turn it off, I can't do anything else with it, right? So usually analog means between a range. So when I looked at the weather today, they gave me a high temperature and a low temperature. That would be analog, because it's going to continuously vary between the low and the high, right? You understand? Digital would be like, what is the temperature at 12 o'clock? We're not concerned with the temperature before. We're not concerned with the temperature below that. It's at 12 o'clock. And that would be an example of digital. So digital is either, basically digital has two states. It's either there or not there. We call them highs and lows. We call them on and off. We call them true, false. They have different things.
Programs then also, like what you said. that, like you said it for a certain time to change, rather than it being.
Yeah, so your alarm clock would be digital. Because it don't alarm all day long, and it don't change volumes, it doesn't do anything like that. What does it do? It goes off at a certain time. And the alarm is either on, or the alarm is either off. That's digital. Now, it doesn't mean we can't change when the digital switch occurs. We call it a threshold. So most of your sensors give you the ability to set what we call a threshold. So you determine what is true and what is false. It's up on the, should be on black. No, I'm sorry, it's not. I just updated the PowerPoints. I realized the PowerPoints, for some reason, had got stripped down for some reason. I don't know what happened to everything. So I was just working on this morning, but I'll upload it to that. So these are different types of sensors. We have sensors that sense presence. And then we have sensors that sense positions. We have sensors that sense metals. We have sensors that sense liquids and solids. We have sensors that sense magnetic fields. We got all different. We have sensors that sense pressure. We have sensors that sense temperature. Right? You understand? And the sensors themselves can be analog or digital. If we take an analog signal and convert it into digital, we talked about this the other day, we go through a device called an analog to digital converter, right? An ADC. Analog to digital converter. And of course, if we're going to go from analog to digital, sometimes we have to go back to digital to analog. So we have what we call a DAC. It actually comes up and makes an acronym. It's a digital analog converter. So if I want to use a computer to control the speed of a motor, then we would have to somehow go from digital back to analog, right? If I want to sense the speed of the motor, then sometimes we go from analog to digital, even though we do have digital speed sensors, which we'll look at in a minute. So to sense the presence of something, which is called, now to sense the presence of something, we're not sensing the position, we're sensing if it's there or not there. Does that make sense? So when I call roll, you're here, I count you present. But when I come up here and I say where are you sitting at, then I'm talking about position, right? So we have two different categories of what we sense. We sense presence a lot. You're saying, okay, is it there or not there? We do this in robotics a lot because that's what we want to do. Does the robot want to move? Well, if it's there, it's not going to move. I mean, if it's there, it will move. If it's not there, it won't move, right? And that would be a presence. Then the presence sensors, we have what we call limit switches, and then so proximity basically means next to. So it's kind of misleading because a limit switch is a proximity switch. But what happened, it's kind of like operating systems for computers. The operating systems can be built into the computer, which is what it is on your cell phones, right? To understand. These computers load their operating system off a device called a disk drive. And if your operating system is loaded off a disk drive, we call it a disk-based operating system, or a DOS. Well, the problem is when DOS first came out, when the first DIS operating systems came out, it was a text-based operating system. And so you had to key in everything. So what happened when they started coming out with their graphical user interface for the shell of the operating system, they didn't want to use the term DOS, so they gave those operating systems other names. And of course, the ones we know about is Windows, right? So Windows is a disk-based operating system on these computers and on my computer right here, but we don't call it a DOS, we call it Windows. So when we use the term DOS, we're talking about the old operating system that came out originally in 1975, right? In fact, it was originally called Control Programs for Microcomputers, CPM. And Bill Gates bought that and developed DOS from that, which is pretty.
Supposedly there's some new technology that is simulated investment right now, and it's not going to take off.
I don't know about that. I have no idea.
I mean, Bill Gates says investment something. I would.
Yeah, but I don't know. You got to be careful about that. Some people throw out ads like that.
Supposedly, if you had invested $10,000 in Microsoft back in the day, it'd be worth like $1,000 now.
Oh, it'd be worth more than that.
Yeah. Like, I think it's like $12.3 million.
I think it'd probably be worth more than that.
That is insane.
Yeah. Like when
I don't know what the return ratio is on that, but pretty high.
yeah, it is. No, I don't know about that. So what we did, even though limit switch is a proximity sensor, it's got its own name. So we have limit switches, and then normally when we talk about proximity switches in the trade, and this is where this guy kind of lets it out, and these are what we call non-contact sensors. So a limit switch, and we'll look at these in a minute, they have to make physical contact with what they're trying to present the presence of. Limit switch. I'm trying to look and see if I got one in my bag. I know I got one in my box up there. So now in the trade, if we use the term proximity switch, we're talking about all these sensors that sense presence without contacting the object. So this is where the book kind of lets us down. So we have all types of proximity switches that the book don't really talk about. They talk about, and the book calls them simple and complex. So, the term is okay, but that's not the term we use in the industry. We call them either digital or we call them analog. Okay. The book says they're either complex sensors or non-complex sensors, or simple sensors. Simple is a digital, and complex would be analog. Now, if you read the discussion in the book, it says these are analog sensors, but you won't see that much. I've never seen that in the trade, and I've been in the trade a long time. I'm not saying you're not going to hear those terms, but I have heard them. So the textbook calls these guys simple sensors. And then the textbook calls these complex sensors. And if you go back when it talks about the portals into the computer, that's the way he defines the ports too. Instead of digital ports and analog ports, he calls them complex and non-complex. But when you get into PLCs, which are basically computers like these things, we don't call them complex and non-complex. We call them input ports and output ports and analog ports and digital ports. So I don't know where this guy got that, but anyway, he explains it, but he don't use the terms that I've heard. So limit switch basically is a proximity switch, but we don't call it a proximity switch. We call it a limit switch because it was the original ones that came out. Sound like DOS. So even though Windows is a DOS, we don't call it a DOS. We call it Windows. And then when we talk about DOS, we're talking about the original operating system, disk-based operating system that originally came out for these computers. So when we use the term proximity switch, we're talking about all the sensors that senses the presence that does not make contact with the object it's trying to detect. That's what proximity is. So the book only talks about the photoelectric, but we have a lot more than that. So we have photoelectric, we're going to look at through the beam, optical interrupters, diffuse, and retroreflective. Then we'll also look at inductive, capacitive, reed switch, Hall effect, and we've already talked about ultrasonic a little bit. Even though I've got one up here, I've got the one off our robot. And I showed y'all the robot. So this is the actual ultrasonic sensor that's on the Lego robot. And then this is the controller right here that we're going to use. And this guy is set up, and we have a section where we can check our sensors out. So people write a program and they think the sensor's not working when there's an option on the controller to check to see if the sensor's working. So I'll show you all how to go through the menus and everything on this, but I'm telling you to check out this ultrasonic sensor. And what it's going to do is going to play a tone. And this is an analog sensor. So what the program's doing is taking this distance and converting it into a tone, right? Can y'all hear it?
Yeah.
Y'all know what a phoneme is?
What?
A phoneme. It's tones that we use to make words. So it's a tone, and we combine phonemes to make sound. We had a robot here at one time that talked in phonics. So you can make that robot speak any language you wanted to do. You could make it sing at you. You could do anything. I just thought about that. So we had one of our guys work with it a pretty good while, and he had that robot cussing. So that's what a phoneme. So phoneme is a tone that we use to make words or make sounds. Now over here on the other type of sensors, so proximity sensors are used to select presence, and then we get into these other sensors that we have force, flow, speed, temperature, which we looked at position, and we looked at those a little bit when y'all came up with y'all's list that we came up with on sensors, right? Y'all did a real good job on that after I forced it out of y'all. This is kind of like an analog sensor. So, the sensor that senses the temperature in your oven has to be an analog sensor, right? Y'all understand that? The sensor that senses the temperature in your house is an analog sensor. Because I can go on my thermostat and it shows me the temperature. It shows it to me in digital form.
But you did say earlier that your thermostat is like
Well, it's not the thermostat, it's when you set a temperature. So when you, the sensor itself is analog. But what we have the ability to do is we can take an analog sensor and we can run it into what we call an A to D converter. So when you say I want my temperature to maintain 70 degrees, then what it's doing is setting the threshold of an analog to digital converter. So when my temperature comes up there and gets to that temperature, it either cuts on my air conditioner or cuts on my heater when it gets to that temperature. So you've got a perfect example of an analog sensor working in a digital world, right? So a thermostat is a really, really good job. It's like the sensor that senses the speed of your car as an analog sensor. Because if it was digital, your speedometer would go from 0 to 100 miles an hour, right? And it wouldn't have anything in between. That would be digital. Either you're going 0 or you're going 100. So the sensor that senses the speed of your car is an analog sensor. But I have a device on there called a cruise control, which is an A to D converter. So it comes up here, we set a certain speed, and when we try to exceed that speed, the car slows down. If we try to increase that speed, it speeds up. So your thermostat has both these. And so what we're doing is if we're going to take an analog sensor and bring it into a digital world, so if I'm going to bring an analog sensor into a computer is digital, the sensor is analog, then we're going to go through a device called a WAD, an analog to digital converter. So a lot of your sensors have that A to D converter built in. All these proximity sensors over here on the left, except for limit switches. Limit switches are truly digital. These are through the beam is truly digital, but this diffused and this retroreflective, these sensors are usually analog sensors that we have the ability to set a threshold on. And I'll show y'all that when we go over and look at some of our manufacturing lines. So ultrasonic sensor, we can use ultrasonic sensor as a digital sensor, or it could be an analog sensor, right? Does that make sense? Everybody okay? Okay, Kristen? Position sensors is the location of an object over a range. And we have different types. We're not going to get into this guy right here. When you get into sensors, we'll talk a lot more about this. The one that you're going to play around with a lot in your career here at Lawson is a device called a potentiometer. Got a case of all this stuff. Don't you hate that? Apple. This has got a knob on it. This is a potentiometer. And we can get these as linear too. So these are rotary potentiometers. Y'all understand the term? Linear and rotary. Linear is a term we use that means straight, a straight line. It's like a linear joint or a prismatic joint on the robot. And then rotary means it moves in a rotation. So what we're trying to sense the position of would be controlling this little knob right here. Of course, this has a fixed range, so sooner or later it's going to, once it hits its end stop, don't go any further than that. But what we can do is whatever we're trying to sense the position of, we come up here and turn this pot, we call this a pot for short, by the way. And what we can do is I can come over here, and all I'm going to do is put this across a 5-volt power supply.
You call this little pot?
The whole thing's the pot. And then, of course, it's got a knob. This is, I gotta get another meter too. My meter stopped working. Plan thing. They had the guy, I forgot who it was, for Apple. They was introducing their brand new phone. And it's got facial recognition on it instead of having the finger thing. And guess what didn't work? It didn't work. So it's one of those things where you check all these things out before you start, and then you get up here and do it, and it doesn't work. So this is a voltmeter that we use to measure all kinds of things. It's actually a digital multimeter. This is analog, yeah. And what I'm going to do is I'm going to go to this thing called a wiper. And I'm going to come up here and turn it. And you see as I turn it, I can get a voltage from basically 0 all the way up to 5 volts. So what would happen is if I was to break this and hook this up to something that was in motion, then the voltage that we get out of it would indicate a what? A position. Are you okay? So I think we showed this on the level detector where they had this pod, and then they just had a rope and a weight, and when the weight moved, it turned the pod, and the pod gave us a voltage that was proportional to the position. And we use these guys a lot. This is analog. But if I needed to bring it into a computer, I could bring it into an analog to digital converter. Right? You understand that? So, okay? So that's a position sensor. Robots don't use these. What robots use is they use something called, this is a pod. This is just showing you the same thing I showed you up here. So we put the pod across a voltage source, and then what we do is we move that knob, we call that the wiper, by the way. As we move the wiper across the pod, across that resistor, we get a different voltage that's proportional to the position of the wiper. Cute animation. This is what the robot uses. The robot uses optical encoders. What's nice about optical encoders, these are digital sensors. So since they're digital sensors, they don't have to convert them from analog to digital, right? You understand? So these are position sensors, incremental encoders, and absolute encoders. The difference between an incremental encoder is an incremental encoder gives you a series of pulses. And as what it's moving, as it moves across, each one of these would equal a certain distance. That makes sense? So what we're going to do is either the device that's in motion is going to move the scale, or usually what happens is the scale is stationary, and that's not true. Or the scale is stationary and the device moves across the scale, which is what most printers do. Printers usually keep the encoder stationary and move across that. Robots move the scale. So the sensors are stationary, and then the scale moves. Now what the absolute encoder does, this is 1, 2, 3, 4. So what it does is it gives us a binary count. So if you learn how to count in binary, what do you think that would equal to? This will equal to 0. What do you think that would equal to? 1. What do you think that would equal to? 2. This is base 2. This is not binary. This is binary. This would be equal to what? 3. This would equal to 4. Some people call it a 1, 2, 4, 8 code. What you do is, if we look at base 2, this would represent a 1, this would be a 2, this would be a 4, this would be an 8. And if I added another digit, it would be equal to 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, right? 8192, 16,164. I can see I've dealt with binary system a lot. But what you do is you just take the previous one and you double it all the time, every time. So all you do is just add the columns. So if this is 1, so this would be 2. This would be 1 plus 2 is what? 3. So this would be 1 plus, this would be 4 plus 1. This would be 5. This would be 6. and then this would be 7. This would be 8. And I could go all the way up till I got this number right here, and this would be equal to 15. And that would be it. That's all I could do. If I added another, so with four binary digits, which we call bits, I could count from 0 to 15. With 5, I could count from 0 to 31. So what we're saying is that this is nice, but what we're doing is we're limited to the number of what they call bands. So you think about the number of positions a robot has. These robots here go well over, 1 million positions. That means I would have to have probably 32 bands, so they don't use this. The incremental encoder, basically the way it works, and they're actually showing the sensors. So these are usually optical sensors. And what they do is down below the bands, they will have a light transmitter. And then up above it, they'll have a light receiver. So as these bands move, they either let the light pass through or block the light. And then each one of those patterns would be equal to a position. What they do on the incremental encoders is they put 2 sensors. So here we'd have to have a sensor for each band. Here we have 2 sensors. And notice they're offset for about 45 degrees. And what happens is if it's moving in this direction, this sensor will see a light before this one. If it's moving in this direction, this sensor would see a light before this one. And so what we get off is we get off a series of pulses that look like this. These would be voltage pulses. And which one occurs first would tell the computer which direction it's moving. The absolute encoder, we don't worry about that because the count is either going to go up or it's going to go what? Down. Now, how do we keep up with positions? Well, what we have to do is we have to bring this into an electronic circuit, and then we have what we call digital counters. And this senses whether it tells it whether to count up or count down. And then how many positions we have would depend on the number of count. How far can these things count to? Now the advantage of this guy is that if I turn off power to my robot and I turn it back on, if the position hadn't changed, it's going to give me back that position. The problem with these, if I remove power from this counter, then the robot would lose its count. And then if I turn it back on, the sucker wouldn't know where it's at. Unless we do something special. What do you think we could do special? Yeah, all we have to do is just come over here and put batteries on these things. And now they'll hold their position. So this is what the robots use over there. Every one of the robots have batteries in the base that holds this count while power is removed. So right now the ABB robot is turned off, but the counters still have their counts because what's in the base of the robot? Batteries. By the way, they call them absolute encoders, even though they're not, because they appear to be absolute encoders to the controller. But if you ever lose those batteries and you turn the controller off and you ever lose those batteries, what's going to happen? You lose the position. The robot is lost. Well, you can. We call it mastering the robot. So if the robot ever loses its position, we'll go over and look at some of these robots. Then what we can do what they call a rough calibration by lining up marks on. Jog the robot and we line up marks. And then we would tell the controller to use that as the origin. That's referred to as a rough calibration. It probably works. I mean, you're going to be able to get that thing within less than a millimeter, which is usually okay for any application. If you got to do what they call what do they call it? It's a more accurate calibration. It's got a name. Then you get a machined jig that you take the tool off and you put it on that robot, and then you move it up against a place on the robot, and then you set the calibration there, which is what they do in the factory. And these batteries has got to be in the robot, because when they ship these things, the robot and the controller are not in the same box. So I need to have the ability to remove the robot from the controller and still not have the robot maintain its origin. So that's part of the preventive maintenance on most robots, is just to go out there once a year usually and do what? Change those batteries. Now what we do, we leave our robots on all the time, except for these two, because they make so much sense. And we'll show y'all. You can see some of them. Some of them are mounted really up in the base. They're hard to get to. Some of them, though, like the FANUC and the big FANUC and the small FANUC, we can actually pop the cover and let you see the batteries. The KUKA is mounted in the back of the robot. The Mitsubishi, the Motoman and the ADV are mounted in the base. So you literally got to take you got to move where all the power cords come. So this is the robots right here. So the absolute encoder, these are rotary encoders. And you can see as these sensors move around, it's giving us basically a number over here that indicates the position. This is 1, 2, 3, 4, 5, 6 bands. So that would be 64 positions that it would be able to give us. But the incremental encoder, when it comes around, so notice when this comes around 360 degrees, it goes back to 0 right there. So every 360 degrees, this guy right here has to start over. So that means anything I'm trying to sense the position of would have to be within 360 degrees of that rotation. That incremental encoder, it's just going to keep pulsing. It gives us a pulse depending on the direction. But we have to have something that counts that, right? You understand? We can count it with a computer, but what the robots use is they actually use physical digital counters in there that counts. But good gracious, with a 42-bit, just 32-bit counters, which would be nothing in digital, we could go up to 1,048,576. With just 32 bits, we can really get up there. Our computers now are 64-bit, right? So we have 64-bit processors. So this is what, and you're not limited to how far these things can spin around, you know. And all we have to do is make sure our counters has enough resolution to keep up with all the positions the robot could possibly get in. So these are digital, and what's nice about digital position sensors is what? We don't have to send them through an A to D converter. We can bring these directly into a computer or the controller of our robot without going through an A to D converter. And they just use those offset sensors on the incremental encoder to give us a direction. This guy wouldn't get lost. This guy could get lost, right? So this is, we call that the origin. So what we have to do is we have to set the origin for the robot. And we do get the ability to set the origin for some of our jobs, what the jobs look like. So we, when I had my accident, we were in the process of moving into this place. And they brought one of our manufacturing lines in, and they left it unplugged. And so it was unplugged the whole time I was gone. I was gone for a year and 3 months. And when we came back, that robot had lost its order. So we got the books out and we looked at the procedure for setting the origin, and we did that. And we set the origin, and it missed everything probably about 6 and about 8 inches. And we did it again, and it did the same thing. So we finally called Festo, come to find out that they had their origin. So you got to be careful with that, because the origin of the robot might not necessarily be the origin that the factory uses. So what they had to do is they had to send us a calibration jig that we had to do exactly what we was talking about. We had to hook it up on the end plate of the robot, and we had to move it down and up to the base of the robot, and we set it, and after that it was fine. The welding robot up in the weld shop, it uses a factory, or it doesn't use a factory origin. It uses an origin that Lincoln welder came up with. So they lost the origin on that robot. They left it unplugged for a long time, and when we did the origin on that, it didn't work either. So we called Lincoln, and they told us that they had redid the origin, and after that, everything's fine. So what we're saying is that that's something you probably need to figure out. If you go into a factory, is do they use the factory origin or do they use their own origin? Of course, if you don't know that, then you need to keep batteries in that thing, right? Especially if you turn the robot off. If we keep the robots on, then it's not using the battery, so the batteries will last a long time. But if you turn the robot off, which happens, this caught us one time in that we don't buy the batteries and we don't keep them spare, because how long they last, by the time we used them, they wouldn't be good anymore. So what we do is we wait for it, because we leave ours on all the time. So the motor man come up and said that it had lost its origin, or the batteries were dead. It never lost its origin. So we ordered new batteries for the thing, and guess what happened before they came in? The power at the college failed. And not only was the encoders backed up, but the memory and the controller was battery backed up. So what happened is we lost everything in that robot. All the programs, all the operating systems, everything's gone out of that robot. Rechargeable batteries have a tendency to, they go out too. So you got a cell phone. Sooner or later the batteries in that thing's going to go out. They always do. Batteries are they're chemical devices. So every battery, I don't care if it's lithium, I don't care if it's NiCad, I don't care what it is, every battery is going to go out sooner or later. So yeah, they do that. Lithium batteries are very expensive, by the way. Lithium batteries are in the ABD. It's supposed to be rechargeable. But when we replace the lithium batteries in that robot, it costs us $250.
Is there any way to make batteries
Yeah, you can go down to Harbor Freight and you can buy a solar charger for your battery.
Really?
You can buy solar charger. Yeah, you can buy those online. You can charge your phone. Now it's not on the phone. It's separate. So if you're into camping and stuff like that, a lot of people buy those solar battery chargers for their cell phone. And you just plug it into your phone just like you would a regular thing. I think they got a solar battery charger that they put on the Corvette out there. Keep it.
Oh yeah.
Yeah, they'll pop it on there and use it to charge the battery if they're planning on doing it instead of trying to run battery charger. That's the only one I've seen. This, by the way, is an incremental encoder. What this encoder does, this was the first robot that the college ever bought. and it had DC motors for that, and then the encoder was on the back. Now what they did is they actually put two encoder notches in here, and then it had two sensors mounted vertical instead of horizontal. And what happens is when the encoder turns in this direction, the sensor hooked up this one would give us a pulse first, and when it turns in the other direction, then the other sensor would give us a pulse. So this is actually the servo motor off one of our robots. Now it looks like this has very poor resolution, but this goes through a 65.5 to 1 ratio. So it means for every 1 revolution down over here, this guy back here makes 65.5 revolutions. So you could take these number of slots and multiply it by 65.5, and that would be the resolution. Here's the actual gearbox right here. Y'all understand that? Which is pretty neat. So it looks like this has very poor resolution, but like we said, for every 1 revolution back here. So I'm back here turning the motor. I don't know if y'all can see the thing turning or not, but it is. So I'd have to turn this 65.5 times for this guy right here to make 1 turn. So to get the resolution, we'd multiply the number of slots times 65.5, and that's how accurate this robot was, which is nothing compared to the encoders on this robot back here. This robot had some limit switches on it, so the encoders were not backed up. So what we did is we just ran the robot until, we jogged the robot until it hit those limit switches, and then that was the origin of the robot. We can't really do that on these robots, so what they do is they just put scribe marks on the robot, or they put indicators on the robot where we can set the origin. So yeah, that robot's no longer around, but it was a chain drive, so it actually changed between the servo motors and the